Here, I would like to introduce the concept of deconvolution factor. What is deconvolution factor? Say we know this fact. The G2 curve is maximized at tau equals 0. At that time, your function value is 1. Okay? And it's very easy because what is definition of G2 function? I of t times I of t minus tau time average, the overlap integral, normalized by I squared t time average. So whenever they are perfectly overlapped, tau equals 0, you got the maxima value. Whenever tau is larger than 0, you only have partial overlap. So overlap integral reduced. And you will have a number smaller than 1. Okay, so it's always picked at tau equals 0. The second fact is your G2 function will always die off, okay, go into 0 if your delay is much larger than your pulse width. Okay, so it means when delay is much larger than the pulse width, I of t and I of t minus tau, the two waveforms will almost have no overlap. So their product is almost 0, and the integration is almost 0. Okay? So if these two facts are true, then we can conclude the correlation width delta tau must be related to the pulse width delta t. They should be of the same order at least. Okay? 也就是说这个 G2 函数的宽度叫 correlation width， 以及原始的函数 I of t， 它的宽度叫 pulse width delta t， 两者应该是接近的，至少是同一个数量级，密切相关的。Okay. So in real applications, one can estimate delta t. Remember, it's only an estimation; it's not precise number. Okay, by the measured correlation width delta tau and a deconvolution factor due to a gaze pulse shape. Okay, before we know how to accurately retrieve the pulse shape, this is something we do not know, right? You can only assume your pulse shape is maybe a Gaussian function or a second hyperbolic function or other functions. Okay. Once the function is fixed, the deconvolution factor is fixed and is defined as the ratio of correlation width to the pulse width. Okay. For example, if it is Gaussian shape, the deconvolution factor is square root of 2, 1.41. And if it is second hyperbolic function, the deconvolution factor is 1.5 something. Okay, it depends on the shape. So you have to assume what is the shape of your signal pulse. And of course, it's not guaranteed. Your assumption might be wrong. And your estimated pulse duration could be different from the reality. So there is a certain uncertainty there. But for well-behaved pulse shapes, this method may have about 10% uncertainty about the estimated pulse duration, which is quite okay in early days. 10% uncertainty is okay at that time. And you have studied the series of active mode locking and the passive mode locking already, right? So what should be the pulse shapes? Gaussian, if it is active mode locking, and second hyperbolic, if it is passive mode locking. So that's why people assume these two shapes mostly. So we only need two deconvolution factors. Okay, then after you got intensity autocorrelation measurement, you have G2 function, you have correlation width. You can use the two deconvolution factors to estimate the pulse durations. So I show you the two numbers, 1.414 and 1.543, if the shape is either Gaussian or second hyperbolic. Okay. This technique is quite okay in early days, because in early days people have active Morlock or passive Morlock lasers to generate femtosecond pulses. But nowadays there are many different techniques beyond active and passive Morlocking. Maybe the oscillators are active or passive Morlocking, but now people rely on pulse compressor a lot. So that means the pulse you actually apply could be something from the oscillator, then after amplification or even compression. And at that time, you may have very different pulse shapes, no longer Gaussian, no longer second hyperbolic. Then this technique could be of certain trouble. Your prediction could be away from the reality, not within 10%, maybe larger. Okay, so certainly we need better pulse measurement techniques. Okay, limitations. What are the troubles suffered by the intensity autocorrelation measurement? First, if you observe the definition of G2 function, okay, it's here. You can see it is insensitive to the phase of A of t, okay, or the temporal phase of the pulse, right? Because G2 function depends on I of t only. If you take I of t, that means you have sacrificed the phase of A of t totally. So there is no information about the phase of A of t. Okay. Then, interestingly, if you take Fourier transform for the G2 function, actually you can show it is the power spectrum. You see absolute square, right? So it means power spectrum of something, I tilde. Okay, but what is I tilde? I tilde is the Fourier transform of I of t. But it is not power spectrum. Be careful. What is the power spectrum? Absolute square of big A. That is your power spectrum. Here, I tilde is nothing about big A. Nothing about big A, because it's Fourier transform of intensity function. This is I of t, not A of t. If this is small a of t after Fourier transform, you got big A of omega, right? The complex spectrum of the signal pulse. But this is not like that. This is Fourier transform of intensity. You got a complex spectrum I tilde of omega, and actually G2 function does not give you I tilde of omega. It only gives you I tilde of omega absolute square. Okay? So what does absolute square mean? It means you lose the phase again. But this time you lose the phase of this spectral function, big I of omega, the spectral phase of I of t. So the first 2 points are different. Okay? 第一点是说，我做了 intensity autocorrelation， 我得到 G2 函数之后，这个我一定没有，就是原始脉冲在时间上的这个复数包络函数的 phase 完全消失掉，看不见。It's a big loss. It's 50% of information, right? 那如果你从 frequency domain 的角度来看这件事，它告诉你呢，你损失的是这个东西。这是一个 spectrum 里面的 phase， 可是这个 spectrum 不是 A of omega. If it is big A of omega, it means you lose the spectral phase. But actually, G2 function has the spectral phase information. You know spectral phase will be translated to pulse duration. And the pulse duration is sensitive. Okay, G2 is sensitive to pulse duration. So it does not sacrifice the spectral phase. It only sacrifices the spectral phase of I of t, the intensity profile. So what's the loss? It's only 25% loss of your information, not 50%. 知道为什么是 25% 吗？第一步，你只看 I of t， 你就剩 50% 了，对不对？你的 A of t 的 phase 一半不见了嘛？哦，你单单为了看 I of t 就损失 50%， 剩一半了。然后呢，这个东西跟它是相等的，可是我的量测甚至没有它，只有它的一半，因为我只有 power spectrum， 是不是一半再一半就是 25%？ Okay, so it means you have only 25% information by intensity autocorrelation measurement, which is even worse than field autocorrelation, right? In field autocorrelation, you have power spectrum, which is 50% of information you need. So mathematically, field autocorrelation gives you more information than intensity autocorrelation. The problem is the 50% you can obtain from field autocorrelation is the same as what you can have from spectrometer, which is usually not so useful. But here, although you have only 25%, but those 25% are useful. It's related to spectral phase and the pulse width. OK， 好，所以我试着用数学的观点告诉你，好像 G2 的量测比较有用，可是就量来看，它没有比较占优势哦，它只有全部的1/4，而 FA 有1/2。那问题是，那1/2是你很容易用别的方法取得的1/2，而这1/4却是你不太容易用其他仪器直接取得的1/4。So G2, the IA measurement is still useful. Okay. Then, G2 function is an even function, so there is no asymmetry information about your pulse shape, which is similar to the case of field autocorrelation. And the same as FA, the requirement of delay scanning prevents intensity autocorrelation measurement from measuring coherent pulse trend with 100% duty cycle. Because you always need a delay which is large enough such that the pulse replicas are totally separated. Then you can get a complete autocorrelation trace. When duty cycle is 100%, it's never possible. Okay, so this is one of the limitations.